Welcome everyone to the Data Science Seminar Series. I'm David Bader, and I'm a distinguished professor at the New Jersey Institute of Technology. And I am hosting the distinguished speaker for today. We're very pleased to have with us Jack Dongarra, who holds an appointment at the University of Tennessee, Oak Ridge National Laboratory, and the University of Manchester. Jack specializes in numerical algorithms and linear algebra, parallel computing, and the use of advanced computer architectures, programming methodology, and tools for parallel computers. Jack's contributed to the design and implementation of many accurate and reliable open source numerical computing packages, including IcePack, Linpack, the basic linear algebra subprograms, or BLAS, the linear algebra package, LAPack, ScalePack, and the message passing interface, MPI. For the past 3 decades, Jack, along with Horst Simon, Eric Strohmeyer, and the late Hans Moyer, have curated the top 500 list, which appears twice a year to benchmark the most capable supercomputers in the world. He was awarded the IEEE Computer Society Sidney Fernbach Award in 2004. In 2008, Dr. Dongarra was the recipient of the first IEEE Medal of Excellence in Scalable Computing. In 2010, he was the first recipient of the SIAM Special Interest Group on Supercomputing's Award for Career Achievement. In 2011, he was the recipient of the IEEE Charles Babbage Award. In 2013, he received the ACM IEEE Ken Kennedy Award. In 2019, he received the ACM SIAM Computational Science and Engineering Prize. And in 2020, he received the IEEE Computer Society's Computer Pioneer Award. He is a fellow of the AAAS, ACM, IEEE, and SIAM, a foreign member of the Russian Academy of Science, a foreign member of the British Royal Society, and a US National Academy of Engineering member. Today, Jack will be talking about an overview of high-performance computing and future requirements. We're very pleased to have him speaking with us today.
Oh, thanks very much, David, for that very kind introduction. I often wonder when I hear that who that person is. It's hard to believe at some level. So what I'd like to do today is talk about high-performance computing and look at some of the future requirements. David already told you about where I work. I'm sitting in Oak Ridge, Tennessee at the moment, in the mountains of Tennessee. Let me just give you an overview here. I'd like to talk about how I got started in high performance computing, look at supercomputing today and some of the trends, and perhaps look at some of the things going on for the future. Okay, so I began my career as an accidental benchmarker in some sense. I was involved in a project when I was just out of my undergraduate education, getting a master's degree. I was involved in a project called Linpack. So Linpack was a National Science Foundation project. It involved Argonne National Lab, where I was working, the University of New Mexico, where Cleve Moeller was working, the University of Maryland, where Pete Stewart was working, and the University of California, San Diego, where Jim Bunch worked. And the way this project was developed, it's a software project to develop software for linear algebra. And we worked independently and came together during the summers at Argonne National Lab outside of Chicago. So that picture is from 1979. I'm the guy on the left with a little bit more hair than I have today. And that's a picture of my car with the Linpack license plate. I was a student at the University of New Mexico working with Cleve Moeller, who's standing next to me on the left, and on the right are Pete Stewart and Jim Bunch. We produced this software package called Linpack. Linpack, again, is a package of software for solving systems of linear equations. It was unique to its time in many ways. It was designed in Fortran. It was intended to be machine independent. It had a lot of features that other software packages didn't have. And it became, in some sense, a standard for how mathematical software would be developed and used into the future. In the appendix of that user's guide, I put together a list of computers running a benchmark of solving a system of equations using the Linpack software. And that list was in the appendix, and it was really the first benchmark report. It came out in 1979, and it benchmarked computers from a Cray 1 down to a DEC, Digital Equipment Corporation's PDP-10. And that list in the user's guide appears like this. There are 23 machines listed there. And you could see the time it took to solve a system of equations. The system of equations was of size 100. 100 was chosen because it fit on all the machines I had access to. The pencil scribbling is what is my scribbling of the execution rate. So the time is given there. We know how many operations are performed in doing that system of equations, and the scribbling was converting that into a megaflop rate. So the NCAR Cray 1 system was running at 14 megaflops for this benchmark, and it goes all the way down, and I can't even read some of the times or the execution rates for some of the machines there. But it was one of the first benchmark reports, and really was the seed for the top 500 list that we have today. Since 1993, we have the top 500 list. Hans Moyer and Eric Strohmeyer at the University of Mannheim maintained the list of the fastest computers, and they ranked that according to the peak performance. So that picture there has Hans on the right, Eric is next to me, and Horst Simon, who joined the group a few years later, is pictured there on the left. And I had a list of a benchmark running systems of equations, and Hans approached me and said, maybe we should merge our two lists and come up with this list of the top 500 using his list of the fastest computers and my benchmark results. So we did that, and we actually had 500 computers in the list by 1993, and it was published as the first top 500 list. So again, it's the list of the 500 fastest or most powerful computers in the world, and it solves a system of equations. It solves a dense matrix problem, and we can argue if that's a good or a bad thing. I'd be happy to have that discussion. Maybe we could do that in the questions and answer follow-up. But back in 1993, that benchmark made a lot of sense. Today, it doesn't quite make as much sense as it did then, but for better or worse, we have that. And there are other benchmarks, and I'll mention a few as we go along. So this has been maintained and updated twice a year. It's updated at the SC meeting that's going to happen in a few weeks in St. Louis. And it's also updated in the meeting that's held usually in Germany in June. So the most recent results we have are from June of this year. Again, the benchmark looks at solving AX equal B for a dense problem. And the idea is you solve the biggest problem you can on your machine. Typically what happens is as you increase the size of the problem, the performance or the rate of execution goes up. And what we want to do is capture the asymptotic rate for your computer. So we're looking for a large problem being solved on your system. And there's a benchmark that you could download and without too much trouble get running on your computer. The benchmark, of course, has been adapted. Back in 1993, there wasn't really parallel computing. We had vector computers for the state of the art for high performance machines. Today, of course, everything is parallel. And the implementation that you could download would be a parallel implementation using MPI as the message passing layer. This chart here gives you a sense of where we've been over the past 28 years with the top 500 results. The red dots are charting the machine at position number 1. So the fastest machine today is here at 442 petaflops. So that's 442 times 10 to the 15 floating point operations per second. And whenever I talk about operations, unless I'm specific, I'm talking about 64-bit floating point operations. It's always 64-bit floating point operations that the top 500 uses. The guy at the bottom of the list is this orange set of dots. Today, that is at 1.5 petaflops. So the entry point for the top 500 list is at that point. And the blue dots are charting the sum of the 500 computers. So that's an Excel sheet computation that's done today that comes out at 2.8 exaflops. So when you take a look at this chart, you see a couple of discontinuities. The first one here perhaps is this discontinuity that occurred around 2008. And another one occurred in this blue line around 2013. Maybe that's slowing down of Moore's law, the end of Dennard scaling. We had an economic downturn around this time, and it could be the influence of less money being spent on high performance computing hardware. I think it's really the collision of all three of those things happening that shows up in this curve here. A couple things to note. I'm giving a talk on an Apple laptop, and I can run the benchmark on that laptop. And when I do, I get 166 gigaflops. That's out of my laptop. That's quite impressive. That would have been on the top 500 list back in 1994. It would have been faster than the fastest machine. The number one machine when this list came out was a thinking machine CM5 with 1,000 processors at Los Alamos National Lab, and that was used for nuclear weapons design. So I have a laptop, or we have laptops today that are much faster than that thinking machine with 1,000 processors in it. And it's quite stunning, the changes that have taken place in technology. This is a list of the top 10 machines today. The top 10 systems really compose 38% of the total performance of the top 500 machines. So this list is really weighted in those the top systems. The number one machine is this machine here at the Riken Computing Center. It's a machine that's called Fugaku. It has ARM processors in it. It has an interconnect that's called the Tofu-D, and it has 7 million cores in it. So 7.3 roughly million cores. It achieved a performance running the benchmark at 442 petaflops. So that's 442 times 10 to the 15 floating point operations. Again, double precision, 64-bit computations. And that reached 82% of the theoretical peak performance for that computer. So the theoretical peak performance is a paper and pencil calculation. You count the number of processors, how much performance each processor is capable of, and that gives you the theoretical peak performance, and then you run the benchmark and see what you actually get. The amount of power needed to run the benchmark, the Fugaku system is around 30 megawatts. And I'll just say that a rough rule of thumb is 1 megawatt year. So if you had a computer in your home and it used 1 megawatt, you would get a bill after 1 year for $1 million. So a megawatt year is roughly $1 million. So that computer in Japan would cost around $30 million just to turn it on. The price of power or electricity is a little bit higher in Japan, so it probably would be a bit higher than that. The last column here is reflecting the efficiency, let's call it. That's the amount of gigaflops per watt. You want that to be as high as possible. And the Japanese machine is about 14.8 gigaflops per watt. And you can see the other machines on the list here. The note here is that if there's a red indicator here that says this machine has accelerators in it, so you see a number of machines have accelerators. NVIDIA accelerators are quite dominant in this top 10 list, but there are other accelerators used as well. The computer in China, the Shenwei Tahu Lite, has an accelerator that's built into the chip, and the Tianhe 2A has an accelerator which was custom built for their system. And we have computers which have built on top of commodity parts. And the machine in Texas is a machine of that nature. So the Frontera system is built on Xeon processors. And there's quite a few of them, 500,000 of those Xeon processors in that system. So that runs out the top 10. The US has 5 systems, Japan 1, China 2, Germany 1, and Italy has 1 system as well. The number 1 system is this machine in Japan. It has an ARM processor. This ARM processor is quite different than the ARM that we have in our cell phones. It's not very power efficient. It consumes quite a bit of power. This one here has 48 computational cores. It has some vector instructions built into the chip. It has an interconnect network, and the performance of one of these chips has a peak of 3.4 teraflops. It does have that vector extensions to it. It is capable of doing 16-bit, 32-bit, and 64-bit floating point operations. It has high density memory built into it, and is quite efficient in that way. The total system, again, is built on top of that node. It has 158,000 nodes in the system. One node has one of those chips, one of those CPUs in it. The total system is composed of 384 racks. It takes up a room about the size of 2 tennis courts. Again, it has 64-bit arithmetic, and the peak is at 488 petaflops. It has 32-bit and also 16-bit capability. 16-bit is used for machine learning applications, and it's around 2 exaflops for those machine learning calculations, the peak performances. This Fugaku system represents 16% of the total top 500 performance, aggregate performance. So it's quite an impressive system. It was designed from the ground up to run computational science problems, and it has a pretty good efficiency for doing that. The number 2 system is a machine at Oak Ridge. It's the Summit machine. It has a peak performance of 200 petaflops. It's built on top of IBM's Power 9 processor. Each node has 2 Power 9 processors and 6 NVIDIA V100 GPUs. And the whole system has 4,600 nodes. It's interesting to note that those GPUs are the things which really give this machine its performance. 97% of the performance of this system comes from the GPUs. So if your application doesn't use GPUs, you're going to be in trouble. You're only going to be able to reach about 2% of the theoretical peak performance for this particular architecture. So using GPUs, structuring your applications to effectively use those GPUs is going to be critical for getting close to the theoretical peak performance for this machine. So a few highlights from the June list that came out recently. The Fugaku continues to be number 1. It was number 1 for 3 times on this list. And again, it represents 16% of the aggregate performance for the top 500 list. And it's capable of performing over 2 exaflops on a benchmark that we have that's used for measuring 16-bit floating point operations. So it has quite an impressive performance for doing 16-bit operations. The top 10 list this time only had 1 new computer, and that's the machine at Lawrence Berkeley National Lab called Perlmutter. It comes from, it's built by HPE and Cray. It has AMD parts as well as NVIDIA accelerators. If you take a look at the top 10 computers on the list, 38% of the performance of the top 500 list is contained there. So again, this list is really quite top heavy in the sense that those machines really dominate the performance of the top 500 list. The entry point has moved up to about 1.5 petaflops. So as to be considered a supercomputer on the top 500 list, you need at least 1.5 petaflops in performance. It's interesting to note that China is the top consumer of supercomputers and also the top producer of supercomputers. So they have a large number of companies which manufacture supercomputers. Let's consider them integrators. They take commodity parts, put them together, interconnect them somehow, and then sell those machines. And companies like Inspur, Lenovo, Sugan are the companies that are China's top producers of those supercomputers. And Intel has the largest share of the top 500 list. So 86% of the machines on the top 500 list use x86, use Intel processors. AMD has another 10%. So 96% of the top 500 list is dominated by the x86 architecture, which I think is really stunning in terms of that list and what Intel or x86 architecture. My guess is that's going to change in the future, but for now, Intel and AMD have that stranglehold on the list. This is looking at that top 500.
Jack, excuse me. How do you count a machine that has both Intel and NVIDIA GPUs?
That's a good question. Right. So we consider that to be an Intel machine. So that primarily Intel processors are driving the machine. The NVIDIA or the GPUs are there to accelerate performance. And NVIDIA has the largest share of the GPUs that are on those top 500 lists. But when you consider the top 500 machines, Intel processors are the things which are really driving it overall. And again, there is a share. I forgot the exact number, but it's about 130 machines use accelerators of the 500. This is a list. This is looking at the countries, and this is what's called a tree graph. The thing on the left is represents 500 rectangles. Each rectangle represents one of the supercomputers on the list, and the area of the rectangle represents the performance that it achieved. So the largest one is this green area here for the Fugaku. That's the #1 computer, followed by the machine called Summit. That's this rectangle, followed by this machine at Lawrence Livermore. And we can go down the list and see those rectangles. So there are 500 rectangles there. And you can see the dominance there. US is dominating in terms of the amount of air or the area on the list, followed by China and then by Japan. If we take a look at the 500 machines and plot them, so we have a plot here of the 500 machines where this is the fastest and this is the slowest machine, we get a graph that looks something like this. And we see that the top 10 machines really dominate. And there's this long tail of machines which evolves. When I look at this list here, in some sense, I wish we would have not the top 500 list, but maybe the top 100 or even the top 50 list to represent supercomputing, because the machines at the far end are really not doing what I would consider large-scale scientific processing. They're being used in a variety of areas, important areas, but not really for large-scale scientific computing. If you take a look at the number of systems that are in a particular country, China dominates. China has 186 supercomputers in the country, followed by the US, then by Japan, France, or by Germany, France, Canada, the UK, Italy, and Russia, with 3 of those supercomputers. So that's quite a interesting list. Is there another question?
Yeah, Jack, how would you rank a cloud machine?
Right.
That has tons of equipment and is capable of doing things.
Right. So we do have in the top 500 list some Amazon systems. They're in the list. They're put there maybe as a stunt. Somebody put together a cloud using a lot of CPUs and GPUs ran the benchmark, and they got an entry into the list. That was a temporary thing, of course. It wasn't sustained over a long period of time. So that might rule them out if we're holding strict to the rules of the top 500 list, where we really want to see persistent machines not put together to run a stunt like that. But there are machines that appear in the list which are cloud-based. This chart here looks at that top 500 list we've seen before, but I just wanted to point out a few things. We reached the teraflop point with the Sandia ASCII read machine, and that was in 1997. We reached another threshold with the first petaflop machine, which was the Roadrunner machine at Los Alamos National Laboratory. And we were supposed to have a machine at Exascale this year, but we haven't seen that machine yet. China says it will have a machine at Exascale in 2021. And there are some rumors that say China has actually achieved that, but they haven't reported that machine yet. And the reasons for not reporting it are unclear. They could be political. There could be some fear of backlash by the US government against China. The US says it'll reach Exascale this year. There's a machine that's being put together here in Oak Ridge, a few miles from where I sit. And that machine will hopefully get to Exascale by the end of the year or by November. I think they're assembling that machine today. I believe they have all the racks in place, and it's just a simple matter of connecting them and running the benchmark. So we'll see how well that shakes out in the next few weeks, to be honest. I've been talking about the top 500 of the Linpack benchmark. We have another benchmark list called the HPCG. So this benchmark is really in response to the question of, is the top 500 list or the Linpack benchmark relevant today? I mentioned when it came out, it was perhaps a relevant benchmark. When the machine went back in 1993, when we started this list, the important thing was floating point computations. That was the thing which took the most time. Today, our machines are over provisioned for floating point. And one of the most critical things in our systems today are really the ability to pass data around. So data movement is really critical. And when we take a look at what people do with our supercomputers today, we see they really are not running dense matrix computations. They're running sparse computations. They're trying to solve large-scale three-dimensional partial differential equations. That solving that system, solving that differential equation leads to solving a large sparse matrix problem. And this benchmark is intended to represent that kind of problem. So this benchmark is solving a large sparse matrix problem. In this context, we're solving a sparse matrix. The sparse matrix is coming about by looking at a three-dimensional problem. There's a 27-point stencil. The matrix has a shape which looks something like this. This is done with my colleagues, Piotr Luszczak and Mike Haru. Piotr's with me at the University of Tennessee, and Mike is at Sandia National Laboratory. Again, the HPCG benchmark is trying to solve a three-dimensional Laplacian. It uses a multi-grid technique for getting a preconditioner, and it goes through a conjugate gradient solver that's exhibited here on the right of this slide. The results from that benchmark are displayed here. This is the top 10 for the HPCG benchmark. The machine at the #1 position is this machine in Japan, the Riken system. For the HPCG benchmark, it achieved 16 petaflops. So that's how much it achieved here for running this benchmark. And as a comparison, you could see what the performance was for the top 500 of the Linpack benchmark. So you can see that there's quite a difference between solving dense matrix problems, the performance you get from solving dense matrix problems, and the performance you get for solving this sparse matrix problem. Dense matrix problems are characterized by doing matrix multiply. So we're doing an operation which has order n cubed operations and order n squared data movement. So you get the surface to volume effect. And with that, it really allows the floating point processing capabilities to shine. And when you have GPUs that are capable of performing those dense matrix calculations very efficient, we get very high execution rates. That's not the case with the HPCG benchmark, where data movement is really a critical thing. And that's why we see this, this difference. And the difference is characterized by achieving only a small fraction of its peak performance. So the computer in Japan achieves only 3% of its theoretical peak performance. And you could look down this list and see that some of our top machines are achieving 1 or 2% of the theoretical peak performance. The computer that achieves the highest performance, highest fraction of peak performance is the number 10 machine on this list. And that machine is characterized by having a vector processor, very similar to the vector processors of the old days of the Cray characteristics. It's a machine from NEC, and it achieves about 5.6% of the theoretical peak. Again, quite low, but very good for this particular benchmark. So this benchmark is really reflective of the kinds of problems people are solving on these large scale systems. They're trying to do computational modeling. That modeling is usually of a large scale three-dimensional partial differential equations that they model using solving a sparse matrix computation, as characterized by this benchmark. So by looking at these two benchmarks, we're going to get a profile of how these computers run. The black dots in this graph represents the theoretical peak performance for the computer. So I'm just looking at the results that we have and plotting the theoretical peak performance, and the green dots are representing the Linpack performance. So that's the dense matrix computation. So here we're running very close to the theoretical peak performance for those machines. The blue dots here are reflecting the performance for the HPCG benchmark. So that's the bottom there, perhaps for performing or giving us a bookends to the performance that you might see on these high performance machines. So again, the green dot is really representing the theoretical peak, close to the theoretical peak for these systems, and the blue is representing what we might consider a practical number being achieved for these systems for these machines, solving a more realistic benchmark. The Department of Energy is heavily involved in high performance computing. This is the roadmap that they have going out to Exascale. The machines that we have here, these machines on the left here, excluding these machines on the right, are the machines that are in place today. These machines, we have 3 Exascale machines that are about to be deployed. The machine at Oak Ridge Frontier is perhaps going to be the first machine in the US to hit Exascale, followed by Aurora, and then by El Capitan, which will be sometimes in 2022 or 2023. So we have, we started this challenge or this path to Exascale way back in 2009. And there were really 4 challenges that we had to get to Exascale. And there were really some concerns whether or not we would be able to reach Exascale given these challenges. So the first challenge would be about energy consumption. So there were research papers in 2008 that predicted an Exascale machine would require something on the order of 150 to 500 megawatts of power. And remember, I said a megawatt year, 1 megawatt year is about $1 million. And that says that to fire up these machines would cost about $150 to $500 million just for the power. So there was a challenge given, and that challenge, there's a challenge given, and that challenge was to get the power consumption down to 20 megawatts. So that was an artificial challenge that was imposed. I think DARPA was the one that raised that challenge and said, you really need to come in at exascale below 20 megawatts. There was a question about reliability. Failures happen, and the concern was that failures would happen faster than we could actually do checkpoints off to disks. And that was going to be a limiting factor in developing a machine, being able to tolerate those failures, being able to have an application stand up and tolerate the failures and be able to run the application to completion in the face of that failure rate. Parallelism was another challenge. We would have a billion-way parallelism. So back in 2009, we thought that we would be able to have that, we would be faced with that challenge. And there was a question whether applications could fully utilize billion-way parallelism within the applications to achieve that exascale. And the last one was data movement, was being able to overcome this memory wall, moving data around and do it in a way that allowed this machine to perform efficiently. So those were the challenges that we faced in 2009 that we had to overcome to get to exascale computing. And the predictions that were made, was that we would have an exascale machine. There was this artificial barrier of 20 megawatts. It was guessed that we would have, the prediction was that we would have 64 petabytes of memory in the system. We would have node performance about this level. We would have the node bandwidth here. We would have concurrency at this level. We would have billion-way parallelism. We would have storage on the order of 500 to 1,000 petabytes. And that the mean time between interrupts was about 0.1 days. And today, what we see in the frontier system is a machine that'll be about 1.5 exaflops. That's what'll be put on the floor in Oak Ridge, and it'll consume about 29 megawatts of power. So we will come in at that 20 megawatt per exaflop threshold that was there. We're going to come in a little bit under the memory system. Memory is very expensive on these machines, and that's one of the reasons for that. The node, I can't give you the node performance because it's still under NDA. The memory bandwidth is about 3.2 terabytes per second. It's coming in with what the guess was back in 2009. The node concurrency is about 100,000 is the node concurrency, and that's coming about because of the use of GPUs. The node interconnect is coming in a bit low, so that's going to be an issue on this machine, being able to move data around in the system effectively to allow this machine to reach exascale. Storage is about in the right limits. And the mean time between interrupts is going to be about 0.3 is what they're predicting per day. So those are the characteristics that we're looking for in the frontier system. So exascale is costing the Department of Energy about $3.6 billion over the next 5 years, over a 5-year window. And the question is, what are you going to get for $3.6 billion? So you're going to get 3 supercomputers, and that's the machines I've mentioned. Each one is about $600 million. The machine Frontier is about that. Aurora and El Capitan is going to come in about that price. You're going to get 21 applications. So these are the applications that DOE are focusing on for those exascale systems. So that's what the exascale computing program is trying to fit on these computers, these 23 applications, and you're going to get a bunch of software. So there's 84 software projects that are being funded by the Department of Energy's Exascale Computer Project, and that software is being put in place to help those applications run. So the applications are really the focus here, It's application driven, and the hardware is being put in place to help those applications reach exascale, and the software is being developed to allow those applications to reach that point. So how did we do on our challenges from 2009? How is Frontier addressing those challenges? Well, as I mentioned, Frontier is going to reach that by coming in at below the 200 megaflops per exaflop barrier. The reliability is going to be there because of having non-volatile memory to allow checkpoints to be done to non-volatile memory, not having to go off to a subsystem to allow the checkpoints to take place if a failure occurs. And if a failure occurs, just that application that has the failure will be taken down. The other applications in the system will most likely continue to run. Parallelism will be hidden within the GPU. So GPU is allowing us to hide some of the parallelism within that machine, so as not having to worry about the details of the parallelism. We're not having to think about doing MPI for machines that have that billion-way parallelism. We can encapsulate that within the GPU itself. And data movement is being addressed by having high bandwidth memory attached very close to the GPUs so that the bandwidth is maximized in terms of moving data around. So those are the 4 challenges. After Exascale, AI for science is the next thing on the horizon. There's been a number of workshops that have taken place and a number of reports that have been written to look at how AI is going to impact science and the challenges and some of the opportunities that it presents have been looked at and are continuing to be looked at in terms of how we address that problem. So, we're not going to stop at exascale. There are plans into the future. So we are thinking about machines that will have 10 exaflops in the 2026 timeframe and have 100 exaflops for AI-based applications, that is doing floating point at 16-bit levels. And then beyond that, we're looking at 50 exaflops in the 2030 timeframe and have basically a zettaflop computer for AI capabilities at 16-bit calculations. And there's a number of questions that are being raised about that. How are we going to be able to achieve these targets? What are the vendors' plans for this? Will AI accelerators make sense in integrating this into the system? And will there be some kind of quantum computing accelerator to help with the mainstream of high performance computing? And those are all questions. I don't have the answers to that. Those are things that have to be worked out in the future. And we're talking about zettascale computing as well. China has proposed having a zettascale system that is 64-bit floating point operations at zettascale. So 10 to the 21 floating point operations per second. We're thinking maybe power consumption on the order of 100 megawatts, the power efficiency at 10 teraflops per watt, the bandwidth, the peak performance per node at 10 petaflops per node, and you can see the other calculations there. So there's a report that's been written that discusses some of those frontiers and getting to exascale computing. AI, of course, is emerging. We see a number of companies that are producing hardware that are specific for AI-based calculations. And what's on the horizon here is looking at exascale being deployed in the 2021 to 2023 timeframe. AI for science and grand challenges are there. There's going to be AI-driven surrogates for the potential for zetta and iota scale performance. We're looking at perhaps AI hardware accelerators for the 2nd and 3rd generation, and quantum computing could break out in the next decade. I'm not exactly sure how that would look, but think of having some attached processor that has quantum capabilities that could be used in conjunction with our standard computational problems and AI-based approach to doing scientific computing. Okay, so I'm coming to the end of my talk here. So hardware is constantly changing. In the early days, scalar and vector processing, that was followed by distributed and accelerators. And we're seeing mixed precision being used more for scientific computations. And it certainly plays a part with AI-based and machine learning. There are three computer revolutions here: high performance computing, deep learning, and I haven't really mentioned edge or AI in detail, but those all contribute to the revolution that's taking place today. There's algorithms and software that are following, but everything really follows the hardware. The hardware is in place. Basically, the hardware is thrown over the fence, and the applications, the algorithms, and the software have to figure out how to fit themselves onto that hardware. So in some sense, there's plenty of room on the top to look at that. There's an interesting paper that appeared last year. Charles Leiserson and company had a paper in Science that talked about looking at the room that's there at the top as a rift off of Feynman's paper or lecture about the plenty of room at the bottom. So with that, I'm going to conclude and ask if there's any questions. I'd be happy to answer them in the remaining time.
Thank you so much, Jack. And there are some questions that came in from the chat. Of course, I have a lot of questions that I'd love to discuss, but let me go to some of the questions that came in. So one of them comes from Ahmed Lashkar, who asks, in Summit, 97% of performance comes from GPUs. Is there a number of what percentage of the power is consumed by the GPUs?
Well, right. So I don't have that at my fingertips, but quite a bit of the power is being consumed by the GPUs. So I would say that the majority of at least half of the power is going into the GPUs. The other half going into the CPUs, going into the memory, and going into the interconnect of that system. But I just don't have a very accurate figure on that.
There's a question from Mert Hidayatoglu, who asks, what happens if I optimize benchmark better for a specific architecture? How would you update the benchmark and/or the results? Okay, so I'm not quite sure how to interpret the results, interpret the question. First off, there should be many benchmarks, so don't misunderstand my talk saying there should only be two benchmarks. We should have benchmarks that look at various aspects of the applications that are intended to be run on this computer. And those benchmarks should have some ground rules on what you're allowed to optimize and how you're allowed to optimize those benchmarks for the specifics of the benchmark itself. There should be ground rules in terms of the accuracy and other things. That all takes place. We have all of those things in place with the Linpack benchmark. There are very specific rules about what you can do and can't do. The Linpack benchmark is about one algorithm, LU decomposition with partial pivoting. That's the algorithm that has to be used. And there are constraints on what goes into the implementation. And you can implement it on the hardware as best you can, achieving a certain accuracy. In the case of the top 500, the accuracy has to be down to 10 to the minus 16 bit accuracy in terms of solving that system of equations. And the same thing is true with the HPCG benchmark. There's a certain accuracy that has to be achieved for that as well. So I'm not sure if I answered the question. So Mert asked another question. Many sparse algorithms are communication bound when scaled out. How do we take the interconnect performance into account, perhaps by looking at end-to-end execution time rather than the peak compute performance? Right. So for better or worse, the benchmarks that we've put together are all
in terms of operations per second, flops per second. So you have to interpolate, you have to understand something about the interconnect and what the impact is of the interconnect to interpret that rate of execution correctly. So for Linpack, it's easy. The interconnect doesn't matter much. It's all driven by doing floating point operations. For HPCG, it's a different story. The interconnect is critical, and we're filtering that through the eyes of looking at the performance rate flops per second. So we're not measuring the bandwidth per se as a measurement. There could be another benchmark which does that. That's just not the way those benchmarks have been structured.
There's a question, interesting question from Saki Burke, who asked, do you see non-von Neumann architectures making it into supercomputers or in-memory computing?
Oh, absolutely. I think they can play an important role as things go forward. The example is quantum computing. That's going to be non-von Neumann based computing. It'll have an impact in terms of high performance computing, perhaps as things go forward. Quantum computing is going to be quite different in terms of the computers that we're faced with today. Quantum computing doesn't give you a single answer. It gives you an approximation to the solution. Of course, we're always getting approximations to solutions, but these approximations from quantum computing are going to be a little bit different than the approximations we've been used to getting with our standard numerical computations that we've been looking at. So quantum computing is certainly there. Neuromorphic computing is another thing that's going to impact or can have an impact. When I think about a computer of the future, it'll have various components to help accelerate the solution time. And those accelerators may be in the form of conventional CPUs, GPUs to accelerate floating point computations. It may be AI accelerators to help in terms of doing the machine learning aspects. They may be accelerators for looking at quantum computing. There could be accelerators that look at performing computations based on optical means. There could be FPGAs. There could be many things that are thrown into the mix. And all of those things could have relevance into the future.
So Taki also asks, Moore's law may be dead or nearing death, but Amdahl's law is alive and kicking. What does this new bottlenecks that become dominant once you accelerate the original ones do the prospects of substantial further bottom line acceleration?
Okay, so Moore's law is not dead. It's slowing down. I think everybody agrees that it is slowing down. We're still increasing the number of gates, transistors on our chips, and that's going to continue into the future. It's not going to continue at the same rate it has. I think that's the point that we have to understand and realize. So it's slowing down. That's going to have an impact in terms of what we can expect out of our conventional silicon, and we're going to have to turn to other things, other means of getting the performance that's going to be expected as we move forward in these things. So I'm not sure I answered the question, nor do I'm sure how to answer the question.
So maybe I can ask or another line of questions. A lot of the talk that you gave was about these architectures, and you mentioned some application areas, for instance, for the Department of Energy, looking at, in the past, the nuclear stockpile and having computational stewardship of it. Are there other application areas that you think supercomputing should get into that it doesn't address today, or some new exciting areas of applications that these new exascales will open for us?
Well, I think the sky's the limit in terms of new applications that could effectively utilize high performance computing, and we see new applications being looked at all the time. The Department of Energy has deep pockets for computing. It's critical to the mission of the Department of Energy, both from the defense side and from the open science side, and that's going to continue to go into the future. NSF has many applications which are different than the ones from the Department of Energy, and they have large computational demands, and those will go forward as well. So I just think that there are many opportunities there. The computing resources are there, they're provided. We see large numbers of applications being run in the cloud. That's another computational resource that's being tapped into. When you take a look at the top 500 list, I would say that there are many applications which are not, or many uses of those machines which are not in terms of scientific computations. We have machines being used in the financial sector. We have machines being used in commercial areas. So there's just many areas where high performance systems are being deployed.
Is this an area where you ever see cloud providers like Google, Azure, AWS, and so on taking ownership for running supercomputers, or do you think that there will always be a need for, say, these specialized labs to run these big machines?
Right, so you can do a cost analysis and see, does it make sense to buy into a cloud computer or buy your own system and run it yourself? So that's been done. There's been studies done. They appeared in some National Academy reports. And the bottom line is it's more cost effective. If you have large computing demands, it's more cost effective for you to deploy a system on yourself and to run that system than to offload that into the cloud, given the cloud economics today. That may change in the future, but that's just the way it is today. If you have certain other constraints like secret information or information that you want to, it's very sensitive that you probably don't want to run in the cloud, that's another reason for deploying your own system. But in terms of the Department of Energy, I don't see them abandoning the use of their own high performance systems and running things in the cloud. I see them continuing to deploy machines that'll be used to drive large scale scientific discovery.
So Jack, thank you again for this fantastic talk with 40, 50 years worth of computing history and also this great outlook for the future. And on behalf of the audience on Zoom, on YouTube, thank you again for just a thought-provoking and quite interesting talk today.
Well, thank you very much. And I'd be happy to follow up with questions. If you have any questions, just send me an email and those questions will be answered.
Take care.
Thanks.